Here in our second part of our Chapter 10 adventure, we have polar coordinates and equations. And these are basically just a special case of parametric equations initially, but we can actually create an entire coordinate system out of these. So what we've been using is the Cartesian coordinate plane. I have two axes, x and y, and every point on the plane can be described using an x-coordinate and a y-coordinate. We call them x, y. But there is another way I can represent every point on the plane, and that is with a polar coordinate system. Pretend those are circles. So what we do, if I want to identify a point on the plane, is I find its direction and its distance. So every point in space, well, space is 3 dimensions, that's a different coordinate system, but every point on the plane, or on a map, I can determine simply by finding out which direction it is and then how far away it is. Except for the origin, which is just going to be the origin. Now, again, we've had some exposure to this already, so I should have said here that this is the point r, comma, theta. We typically represent those with the r, or the distance, or also called the modulus, or magnitude, first, and then follow that with the angle. Now, it's fairly easy to translate between these two coordinate systems because the polar coordinate system basically works on circles of radius r, and I can find coordinates in the Cartesian plane on a circle of radius r simply by using sine and cosine. So we have x is equal to r cosine of theta, and y is equal to r sine of theta. So if I know my polar coordinate, I can easily change to a Cartesian coordinate. For example, if I go from r comma theta to x comma y, and I have the point 4 and 4, or pi over 3, then this is going to map to x is r cosine theta. So this would be 4 times cosine of pi over 3, and y is equal to r sine theta, so this is 4 times sine of pi over 3. But this simplifies, of course, because cosine of pi over 3 is a half, so this is 2, and sine of pi over 3 is root 3 over 2, so this is 2 times root 3. But what if I have Cartesian points and I want to describe them using polar? And then it becomes a little more ambiguous, because this x, I need two variables. My one x isn't going to translate immediately to two variables, so I have some slightly different equations I work with. I'm going to use, well, if I have x squared plus y squared, that's equal to r squared cosine theta plus squared plus r squared sine squared of theta, which is r squared cosine squared theta plus sine squared theta, but that's an identity and that's equal to 1. And as far as pulling out the angle, I'm actually going to use tangent, because tangent of theta should be equal to let's see, that's sine over cosine, so this is equal to y divided by x. Or arctangent of y over x is equal to theta. But what we're going to see is that there's a little bit of a problem with polar coordinates because there are many different representations for a single point, versus in the Cartesian coordinate system, there's only one per point. So if I wanted to go from 2, 3, so if I want to go from x, y to r, theta, and I want 2, 3, then this is going to go to this r squared is x squared plus y squared. So this is the square root of 4 plus 9, comma, arctangent of y over x, which is 3 divided by 2. But arctangent, the range of arctangent is only between negative pi over 2 and positive pi over 2. And technically, if I take the square root to find out what the r is, I should have a plus or a minus there. So the ambiguity is present. Because you see, the way polar works is you choose a direction and then you choose a distance. But you're also allowed to choose negative distances. So not only do you have coterminal angles working with you, but you can also go backwards to try to find your point. So for example, this point we found earlier, that's an ugly point. 4, pi over 3. Pi over 3 is up this way. We'll say that's 4, pi over 3. Well, this is also negative 4, 4 pi over 3. Which is also negative 4, negative 2 pi over 3, which is also 4, let's see, that's up negative 5 pi over 3. Because I can go up to this angle, pi over 3, and then go out by 4, or I could go all the way around to the opposite side and go backwards by 4. So technically speaking, going from x, y from Cartesian to polar, you have infinitely many answers, which is just great. But the benefit is all of them will be correct. However, if we need to do some type of specific work, like with functions that we'll get to, you'll have to be a little bit more careful. And you want to make sure you stick to maybe the domain the function is defined on, or stick to small angles and positive radii. So we can define functions on our new coordinate system, and instead of giving y as a function of x, we're going to be using the radius as a function of theta. So you tell me which direction you want to point, and then I'll tell you how far away to place your point. Which works a lot better than trying to say how far away do you want to look and then choosing an angle later. Although you could probably try to make that work. So for a really basic function, we could have r of theta equal to 2, a nice constant function. So what this says is that the radius, or the modulus of my point, given an angle theta, is always equal to 2. So what that traces out is a circle of radius 2. Which is a much, much nicer equation, don't you think, than having x squared plus y squared equal to 4. Similarly, if I forego the y entirely, I could have theta equal to pi over 4, and that would hold true for all r values. So this would actually be the line just pointing in the direction pi over 4. So this is similar to the line y equals x. And I should say this one is similar to x squared plus y squared equals 4. But what if I wanted some other line in polar? Well, then what I would have to do is I would have to translate a Cartesian line, which I can understand easily, into a polar line. So I want to translate the line y equals negative 1/2 x plus 2 into the polar coordinate system. But what I would do is I would use exactly those equations I wrote up above, where my x was equal to r cosine theta and my y was equal to r sine theta. So this means I get r sine theta is equal to negative 1/2 times r cosine theta. Plus 2. Now I don't know what r and what theta are, but I also didn't know what x or what y were. So what I have now is technically a function, but I should try to solve it for r so that I have a proper function, r of theta. So let's see, I can add 1/2 r cosine to this side to get all the r's on one side. And that will be equal to 2. I can factor out this r. And then I can divide. So I'd have r is equal to 2 divided by sine of theta plus 1/2 cosine of theta. Which looks a lot more complicated than just having a simple line, but that's both the danger and the benefit of having different coordinate systems. What looks very complicated in one coordinate system might be very simple to express in another coordinate system. Or, the other is also true, what might be very simple to express in one coordinate system could be very difficult to express in the other. So this comes up a bit in Calculus 3 because given some horrible integral or multiple integrals, you might be able to translate your problem into a different coordinate system. So you might have this nasty unintegrable function, but when you retranslate your problem into a different coordinate system, like polar, or its Calculus 3 is three-dimensional, cylindrical or maybe spherical coordinates, you might have a very easy to look at integral that you can easily find the antiderivative of. So I don't want to try to draw that line based on its polar equation, but it's there. But what I would like to draw is some other polar equations. Let's take, for example, r of theta equal to 3 sine of theta. Then what do we do here? Well, we don't have much choice with these because it's such a strange coordinate system. All we can really do is start plotting out points. So, fortunately, we are masters of the sign chart. So, if I plug in theta equal to 0, I get 0. Right, good. If I plug in pi over 6, I get 3 times sine of pi over 6, which is equal to 3 times 1/2. So I'll say 1.5 is right here. That means I'll have 1 here, 2 here, and 3 here. If I plug in pi over 4, I get 3 times root 2 divided by 2. So that's about 1.5 times root 2, which is kind of sort of about 1.5 times 1.5, so we're going to kind of get about 2.25. So I'm just going to say that that's a little bit over 2 because I don't have much at my disposal. And if I plug in pi over 3, Well, 3 times sine of pi over 3 would be 3 times the square root of 3 divided by 2. The square root of 3 is about 1.7. And so 3 of those is about 5. So we get 2.5. But then when I plug in pi over 2, I actually end up getting 3. But then after this, sine kind of starts to go back down, and I'm actually going to end up getting a mirror of all of the points I've already plotted so far. And so what I should end up seeing is, as I plot from 0 to pi, is I get a circle. Plus 1 for art. So r of theta equal to 3 sine of theta. We can actually demonstrate this for sure without my horrible artwork. But this is a circle of radius (3 over 2) and center 0, 3 over 2. If I had instead done a cosine instead of a sine, then my center would be on the x-axis instead of on the y-axis. And this is on the domain 0 to pi. But what will happen if I go past pi, then my sine values are going to be negative. And so I'm going to have a similar reference angle down in this direction, but I'm going to have a negative radius, so it's going to point back over here. So on pi to 2 pi, r of theta equal to 3 sine of theta will retrace the points from 0 to pi. So instead of from, I'll just say on. So this would be a function which only has a period of pi, even though sine of theta by itself has a period of 2 pi. So this is a good example to say, just because you have a polar equation with some kind of trig function in it doesn't mean that you're going to have the right period. Because this one started to repeat itself after pi, even though sine of x on the Cartesian system, that repeated itself after 2 pi. Pi was only half of the original period. Another one of my favorites, r equal to 1 plus 2 sine of theta. So let's see what happens this time. If I plug in if I plug in 0 for sine of theta, I'm going to actually get 1 this time. So let's put 1 out here. If I plug in pi over 6 for sine of theta, I'm going to get 1/2. So that's 1 plus 2 times 1/2. I'm going to need to move this down a bit because I know what it's going to look like. Alright, back to where we were. Sine of pi over 6 is 1/2, so r of 1/2 is going to be 1 plus 2 times 1/2, which is 1 plus 1, which is 2. So if 1 is about here, that means 2 is up here. If I plug in pi over 4, I'm going to have 1 plus 2 times root 2 over 2, which is going to be 1 plus root 2, which is about 2.5. So about here. And if I plug in pi over 3, that is going to be 1 plus root 3, which is even more. Let's see here. Let me try to... Okay, so if I get to 3, so maybe this 2.5 should have been closer over here. And then at pi over 3, I'm almost 3. But then at pi over 2, I'm equal to 1 plus 2, which is 3. Alright, so it looks like so far I'm doing something kind of circular-ish. Let's see, now what happens if I go from pi over 2 to pi? Well, that's when the sign repeats itself. Oh boy, so let's see if I can replicate this. That's not bad. Now what happens as I plug in values down here? Well, sine of, that's pi plus pi over 6. Sine of 4 pi over 6? No. 7 pi over 6. Sorry, this is after pi. So sine of 7 pi over 6 would be 1/2, but it would be a negative 1/2. So 1 plus 2 times negative 1/2 is 0. So that means I connect in like this a bit. Let me try that again. I connect in like this. As sine goes to pi over 4, I'm going to have 1 plus 2 times root 2 over 2. 1 plus 2 times negative root 2 over 2, which is 1 minus root 2 over 2, which is now a negative 0.414. So I'm pointing this way, but I have a negative radius. Now if I go down to 4 pi over 3, sine of 4 pi over 3 will be negative root 3 over 2. So that's 1 plus 2 times negative root 3 over 2, which is 1 plus negative root 3. And this is at negative 1.7-ish. And then as I reach not negative, but 3 pi over 2, my sign will be 1 plus 2 times negative 1, which is 1 minus 2, which is negative 1. So when it's pointing this way, I have a radius of negative 1, so up here. And that continues until I get to 2 pi. And that's going to continue until I get to 5 pi over 6, 11 pi over 6, as this is going to get mirrored again. And then the last leg from 11 pi over 6 back to sine of 2 pi, well, that's going to be equal to 1. So this curve is called a well, it's a similar class to a cardioid, but it's called a limacon. So an interesting exercise would be to try to find the area inside of the loop or the area inside of the outer shell. One more. If r is equal to sine of 3 theta, then I'm going to get what is known as a rose curve, and it's going to be with 3 petals. If I have an even number in there, then it's going to have twice as many petals. So let's see. Sine of 0 is 0. Great. Sine of 3 times pi over 6 would be the same as sine of pi over 2, which is 1. I'll put 1 right here. Now if I plug in pi over 4, I get sine of 3 times pi over 4, which is sine of 3 pi over 4, which is up here, so that's root 2 over 2, which is down here a little bit. Further down than that. And if I plug in pi over 3, that's sine of 3 times pi over 3, which is sine of pi, which is actually equal to 0 again. So it looks like I've gone up and then come back. So what happens as I go to pi over 2? Well, sine of 3 times pi over 2 is sine of 3 pi over 2, which is equal to -1. So if I'm pointing this way, my value is -1. So I actually went all the way down here. Now, if I go to, what's next? Sine of 2 pi over 3, that'll be sine of 2 pi, so I actually get back to 0. Now, if I get, after pi over 3 is 3 pi over 4. Sine of 3 times 3 pi over 4 is sine of 9 pi over 4, which is more than 2. That's past full circle, so this is equal to sine of regular pi over 4. And sine of regular pi over 4 is square root of 2 over 2. Which was here-ish. And then when I hit sine, if I plug in 5 pi over 6, sine of 3 times 5 pi over 6 is sine of 15 times pi over 6. Minus 2 pi, that reduces to sine of 3 pi over 6, which is sine of pi over 2, which is 1. And then if I plug in sine of pi, I'll have sine of 3 times pi, which is sine of 3 pi, which is equal to 0. So it looks like I went back up this way and made another loop, and then went back to 0. So this is called a rose curve. 3 petals. And in general, actually let me make a remark. This, the limestone had a period of 2 pi, but this rose curve I just did had a period of pi. Because just like the circle that I had before, which I guess you could consider to be a single petal rose curve, if I go past pi, all my sine values will end up being appropriately negative, and I'll just retrace the rose curve the way I already had it. So rose curves in general, it doesn't matter if we have sine or cosine, it just changes which axis it kind of starts on. If r is equal to sine of 2n theta, so if this number is even, we have 4n petals total. And the period should be 2 pi. However, if r is equal to sine of 2n plus 1 theta, So if I have an odd number of petals, then I have exactly that many petals, and the period is only pi. Which helps to tell you what kinds of things you can expect if you're graphing something, just in case you find a mistake to catch. So finding slopes at a point, when we're talking about slope, we are talking about Cartesian slope. So if I'm looking for the slope at a point on a curve, then I'm just going to use exactly the formula, I guess, that I did for parametrics. But I should make the remark that even though I'm finding a tangent line, which has a slope in the Cartesian sense, this is not going to represent the derivative in the polar coordinates. This will have a rate of change, and it will be a rate of change of the radius based on the theta, but this isn't going to match up exactly with the slope of a line that I'm about to calculate. So from parametric, because these are parametric, my dy over dx, the slope of a tangent line, is equal to dy over d parameter, which is theta, over dx over d theta. But this is equal to d theta. Y is equal to r sine of theta. And x is equal to r cosine theta. Now what happens here, since r is also a function of theta, if we're talking about polar functions, I'm going to have to do a product rule on these guys, leaving me with, on the top half, dr d theta sine of theta plus r cosine of theta. And on the bottom, again from product rule, I'm going to have dr d theta cosine theta plus, minus, because the derivative of cosine is negative sine, r sine of theta. Which looks pretty ugly, but we're going to make use of it in the next section, which is section 10.4. So, moving right along up the calculus ladder, I technically have slopes, but they won't be quite. I have the slope of a polar function in a Cartesian system, but the slope of a line in the polar system is usually only used when you need something about the rate of change. It's a little hard to think about slope in a polar sense. So the question we want to ask is, how do we calculate areas in polar? Well, we do that with the area of a sector of a circle. So sectors of a circle are kind of like the rectangles from Cartesian system. So if I take a narrow enough angle, or narrow enough difference in angles, then I'm going to be roughly circular with an appropriate radius. Now the area of the sector of a circle can be calculated by finding the area of the circle, pi r squared, and multiplying it by the angle you're using divided by 2 pi. So this fraction over here on the right, this represents the proportion of the circle which you are using for the area. But here the pi's cancel, and I actually end up with 1/2 r squared theta, if I'm looking at that right. So if I've taken an area here, then I'm going to slice it up into a bunch of, like pie slices. And the width of each slice, or rather the angle of each slice, is going to be delta theta. So you kind of see where I'm going with this. The area is approximately equal to the sum from I equals 1 up to n of 1/2 times r of theta sub I multiplied by delta theta, or in terms of an integral, after I apply a limit to this Riemann sum, the area in polar is given by 1/2, forgot to square this in the sum, r of theta squared, oh jeez, I said integral, and I wrote a sum, integral from a to b, d theta. Much better. Or, if we're feeling particularly lazy, the area is given by the integral 1/2 r squared d theta. So we should probably pick one of these to find the area of. The first one was r equal to 3 sine of theta. Well, we graphed that before, and that actually, I claimed that that was a circle of radius 3/2. Which should have area pi times 3/2 squared, which is equal to 9 pi over 4. So we'll see if I get that by doing this integral. Now I said that the full curve was traced out for that problem from 0 to pi. So I'm going to do a full integral from 0 to pi of 1/2 r squared d theta, which is equal to the integral from 0 to pi of 1/2 r is equal to 3 sine of theta squared d theta. Which means here I've got, I can factor stuff out. I'll have a 9/2 integral from 0 to pi sine squared of theta d theta. And we've done these before. This is 9/2 multiplied by, this is 1 minus cosine, no. This is 9/2 times the integral from 0 to pi of 1 minus cosine of 2 theta divided by 2, which is equal to, let's see, 9/4 integral 0 pi 1 minus cosine of 2 theta d theta, and I can do that antiderivative. That's theta minus sine of 2 theta over 2. Yes, that's from 0 to pi. But when I evaluate this, I get 9/4 times pi minus 0. Well, let's just do it this way. Pi minus sine of 2 pi is 0, minus 9/4. 0 minus sine of 0 is 0. So this cancels off completely, and I get 9 pi over 4, which is exactly what I was expecting to get, seeing as how the thing I drew was a circle. So sometimes we're going to have curves which might intersect themselves, like the limaçon I drew, or you'll have two curves and you want the area between them. You need to find out where they intersect. But you have to be careful because they might not intersect for the same angle. So look at number 31, I'm pretty sure is one, has intersections, but not at the same angles. I think a really easy comparison for this is, in general, let me see. also, if I have r1 equal to sine of theta and r2 equal to sine of 2 theta, one of those has a period of pi, but the other one has a period of 2 pi. But they are going to have several intersections. But these intersections will occur at specific r comma theta coordinates, but they will not intersect at the same times that I reach them on the curves. So what you have to do is you're going to have to set up two different integrals with two different sets of bounds to properly represent the areas that you're looking for. Because while one of them might be equal to, 1/2 comma theta, the other one might be equal to negative 3/4 comma theta is the thing I'm trying to illustrate. So as a rule, always draw the graph when you can. Because you need the graph to determine the bounds. So, as an interesting problem, you should attempt to take the area of a limaçon. You can either use the one I provided up above, or you can look at problem number 21 in the book. It's this of section 10.4, which is actually the same function. So lastly, since chapter 8 was all about finding arc lengths, and the first two sections we found more arc lengths, guess what we're going to do for this section is we're going to find more arc lengths. So this works exactly the same as it did in parametric. The ds, well, the arc length is equal to the integral of the dx, and the ds can have different representations depending on, well, first, what kind of coordinate system you're working with, or two, whether or not you're using parametric. But since polar kind of counts as parametric, we have this. It's dx over ds, over d theta squared plus dy over d theta squared d theta. But we have actually calculated what dx and dy over d theta are equal to. So we have a nice big square root. This is dr over d theta cosine theta minus r sine theta quantity squared plus, that's the dx, and dr d theta sine of theta plus r cosine theta quantity squared, that's the dy. And what I should do is add on the d theta. So what do we get when we expand all of this? What we get is tons of fun, but we'll have a big square root, and I know I'm going to end up with a bunch of stuff because I just did this. I'm going to have dr d theta squared cosine squared of theta minus 2r dr d theta sine of theta cosine theta which I could rewrite as probably sine of 2 theta, but I don't think it'll help yet, plus r squared sine squared of theta. Alright, plus the other one from the dy's. I'll have dr d theta sine squared of theta, this should be squared, plus 2r dr d theta sine times cosine, plus r squared cosine squared of theta. There's a d theta waiting patiently outside. But these cancel to minus 2r dr sine of theta and plus 2r dr sine of theta. But also, sine squared plus cosine squared is equal to 1. So if I factor out the r squared, I'll have sine squared plus cosine squared, so that's 1. And the same over here, leaving me with the much nicer dr d theta squared plus r squared d theta. That's my ds. So if I wanted the arc length, for example, of the top half of the loop of that rose curve, I should go back to the picture to verify my bounds. This top loop was drawn out from 0 up to pi over 3. So I want to find the arc length of one loop of r equal to sine of 3 theta. But what did I get out of that was this is the interval 0 up to, not 3, but pi over 3. So all I have to do really is do an integral from 0 to pi over 3, and I want the ds, which is dr d theta squared plus r squared. But check this out. I go from integral 0 to pi. Dr d theta is equal to 3 cosine of 3 theta squared plus sine of 3 theta squared d theta. That's 0 to pi, big square root. I have 9 cosine squared of 3 theta plus sine squared of 3 theta d theta. But as is usual with a lot of arc length problems, I don't think we'll actually be able to integrate this one. If that 9 wasn't there, this would be a really easy problem. But since we do have a 9 there, this is probably going to kind of suck. So that's basically it for polars. Certainly take the time to try a bunch of the book problems, or even just grab a calculator and try drawing a bunch of these pretty pictures. Arc length integrals can usually end up being kind of tough, but that's just the nature of those. I certainly recommend you try the challenge and number 31 in a textbook if it's not already part of the WebAssign.